Again, welcome to Operating System CS332 class. And this lectures cover chapter 6 of our course textbook. That is concurrency, deadlock, and starvation. So first we start with the definition of deadlock. And here we say that deadlock is a permanent blocking of a set of processes that either compete for system resources or they communicate with each other. So a deadlock normally can be defined again as a permanent blocking of a set of processes that either compete for system resources or communicate with each other. So a set of processes is deadlocked when each process in the set is blocked, awaiting an event. We say typically by freeing up of some of the requested resource that can only be triggered by another block process in the set. So a deadlock is a permanent because none of the event is ever triggered. And unlike other problems, in concurrent process management, again, there's no efficient solution in the general case. So here we have an example of a deadlock possible. We can see we have 4 ways, and as the cars approaching the intersection, you can see all of them want to approach at the same time. And the second section again, we can see the deadlock, they all approach at the same time. So all deadlocks normally involve conflicting needs for resources by 2 or more processes. So when we have 2 or more processes and there's a conflict needs for them, then there will be a deadlock. Again, a common example, as we said, is the traffic deadlock. And the diagram shows a situation in which 4 cars have arrived at 4-way stop intersection at approximately the same time. Now, the 4 quadrants of the intersection are the resources over which control is needed. In particular, if all the 4 cars wish to go straight through the intersection, the resource requirements are as following. So let's say car 1 travel north needs quadrant A and B, and also car 2 needs quadrant B and C. Okay, B and C. And also car 3 will need a quadrant C and D, C and D. Then car 4 needs the quadrant D and A because it's going straight. So car 1 need A and B, and 4 need D and A, 3 need C and D, and 2 need C and B. So the rule of the roads normally is that a car at a 4-way stop should defer to a car immediately to its right. And this rule works if there are only 2 or 3 cars at the intersection. So again, that's the whole concept of deadlock. So in terms of, again, resources, 2 processes want to one want to receive, or we want to keep the resource, and other process also the same resource you want to receive. So we have 2 processes who want to use the same resource at the same time. If there's no communication, there can be a deadlock. So let's see this example. Maybe we'll give us more detail. Now let's look at this example here. So here we have something called a joint progress diagram. So we can see the progress of Q going towards up arrow. Then we have the progress of P to the lower right side. So we have a P and Q at this section. We can see that again, P and Q needs resource at the same time. So the diagram show here, so both, the first diagram show both P and Q want resources A. So P and Q need resources at the same, resources A at the same time. And at this session also P and Q need resources B or want B at the same time. And here we're going to have a deadlock because we can see the two arrows coming towards. So here we say the x-axis represent the progress at the execution of P. You can see the progress at the execution of P as we said. And also the y-axis represent the execution of Q. Now the joint progress of the two processes is therefore represented by a path that goes from the origin in the northeastern direction. So for uniprocessor system, only one process at a time may execute. And also the path consists of alternating horizontal and vertical segments, with horizontal segment representing a period when P executes and Q waits. And the vertical segment will represent when Q executes. Horizontal means when Q executes, P waits. The figure indicates area in which both P and Q require resources A. So that's the section here. And also resources B, both P and Q. Because we, again, assuming that each process requires exclusion control of any resources, these are all forbidden regions. And that is, it is impossible for any path representing the joint execution progress of P and Q to enter this region. So the concept of, again, mutual exclusion. So for example, here we can say that when Q acquire B, then A, then release B and A. Then when it release B and A, then when P will resume its execution. And it will be able to acquire both resources. If Q again acquire B and then A, and then release B and A, when P resume execution, it will be able to acquire both resources because again, Q has released both of them. Now, when Q also acquired B and then A, P executes and blocks on the request for A. Then Q releases B and A when P resumes execution. It will be able to acquire both resources. That's Q again acquires the B and then A. Then P executes and blocks on the request for A. But when Q releases both B and A, then P can resume execution. So the whole concept we are trying to say here is avoiding the deadlock. If P is using the resources A, then Q have to wait. When P releases it, then Q can use it. So in general, we said here that possible progress path for P and Q. Horizontal portion of path indicates P is executing and Q is waiting. And vertical part will be when Q is executing, then P is waiting. The goal of this rules here again is to avoid the deadlock. Now, if P is executing and with Q at the same time, they are requiring for a service, there's a possibility when both, that's 3 and 4, both of them may have deadlock can occur in this area. So again, whether or not deadlocks occur depends on both, again, the dynamics of the execution and on the details of the application. So again, this situation is reflected again in this diagram. Some thought should be convinced as that regardless of the relative timing of the two processes, deadlock cannot occur. So the joint progress diagram can be used to record the execution history of the two processes that share the resources. In cases where more than two processes may compete for same resource, then we need a higher dimensional diagram required. The principle of, again, concerning the fatal region and deadlock will again remain the same. So here again, we have both A and P want the resources A, and both P and Q want resources B. Now, in this area, we can avoid a deadlock when P is executing, again, as we said, Q waits, Q executing, P waits, if they need that same resource. So here we can see when B release, A will get it and keep going. So next we talk about the resources categories. And here we say there are two general categories of resources that can be distinguished. We have the reusable and also we have the consumable. So a reusable resource is one that can be safely used by only one process at a time and is not depleted by that use. That's why again it's reusable. So this can be safely used by only one process at a time, and most important, it's not depleted by that use. Now, processes obtain resources units that later release for reuse by other process. So example of reusable resources can include the processes or I/O channels, or even the main and secondary memory devices, and other data structures such as files, database, etc. Now, a consumable resource is one that can be created, that we can produce and also destroy, consume. So example of a consumable resources are interrupts, signals, messages, informations, and even the I/O buffers. This can be created and also destroyed. So those are the two categories of resources. We have reusable resources. As we said, example can be the I/O channels. The main memory can be reused over and over. Devices, the example can be I/O devices, the CPU, etc. But consumable, again, is the one that we can create and also we can destroy. So a very good example would be the interrupts, the signals, messages, and informations. So we have an example here of a deadlock involving reusable resources. So consider two processes that compete for excessive access to a disk file, let's say file D. So we have the steps process PO up to P6. The first action is to request for the file D. And also a tape drive T. So T represents our tape drive. So we have two processes again, P and Q. So PO requests first. Then when we request, we lock it. Then we request for T, we lock it, then perform a function. Then we unlock D and T. Now with the process Q, we request T, then we lock T, then request D, we lock D, then perform action, then unlock T, and then unlock D. So yeah, this is a very good example of involving reusable resources. The program will engage in operation that's shown in the slides here. Deadlock occurs if each process holds one resources and requests the other. For example, deadlock occurs if multi-program system interleave the execution of two processes as follows. So let's say, for example, we have PO, then we have P1, then QO, Q1, then P2, Q2. Again, that will be a deadlock will occur. So if I have these two, for example, Process Q have request for T and it have T, and it's requesting for D also, but it's not releasing the T. So this may appear that this is a programming error rather than problem of OS designer. However, if we have seen that concurrent program design is challenging, then such deadlocks do occur, and the cause is often embedded in complex program logic, again, making detection difficult. One strategy for dealing with such a deadlock is to impose a system design constraints concerning the order in which the resources can be requested. And I think that's very important to avoid a deadlock. Another example here of a deadlock with reusable resource has to do with the request for main memory here. So memory requests. Suppose the space available for allocation is 200 kilobytes, and the following sequence of requests occurs. So we have P1, then request 80 kilobytes, request 60 kilobytes. P2 request 70 kilobytes and request 80 kilo. And remember, we have 200. Now, deadlock occurs if both processes progress in their second request. Because here, if the amount of memory to be requested is not known ahead of time, it is very difficult to deal with this type of deadlock by means of system design constraint. So again, the best way to deal with this particular problem is, in effect, to eliminate the possibility by using virtual memory, which again, we're going to discuss in our future lectures. And the problem here that we don't know the actual size from beginning. So we have 80, 70, the third time, that's 150. The third time we are having 60 and 80, it passes the 200, the limit. So a deadlock occurs in both process progress to their second request. Now, if the second request is, let's say, only 10 kilobytes, then it's within the 200 range, so that should work. Now, a consumable resource deadlock, here we consider a pair of processes in which each process attempts to receive a message from other process and then send a message to the other process. So receive and send. Deadlock occurs if the receive is blocking. So this is again an example of a deadlock involving the consumable resources. And the deadlock again occurs if the receive is blocking. The receiving process is blocked until the message is received. Again, once again, a design error is the cause of the deadlock. Such error may be quite difficult to detect. Also, furthermore, it may take a rare combination of events to cause the deadlock. Thus, a program could be in use for a considerable period of time, even years before the deadlock actually occurs. So again, deadlock approaches. Here we say again, there's no single effective strategy that can deal with all types of deadlock. We have different types. But we have three approaches that are very common here. The first is the deadlock prevention. This would disallow one of the three necessary conditions for deadlock occurrence or prevent circular wait condition from happening. And deadlock avoidance, here we make sure that we do not grant a resources request if this allocation might lead to, again, deadlock. And then the deadlock detection, we should grant resources requests when possible, but periodically we need to check for the presence of deadlock and take action to recover. And again, we are going to examine each of these in turn and in our few slides to come. So here we can see A, we have P1 requesting the resources RA. So resource requested. And then resource is held by P1. Now in the circular weight, we can see P1 request for resources, but P2 is held by it. And also P2 requests resources of RB and also is held by P1. So process 1 needs some resources, but is held by process 2. Process 2 also needs some resources, but that resource is also held by process 1. So this is called the concept of, again, circular weight. So again, the useful tool in characterizing the allocation of resources to process is the resource allocation graph. So the resource allocation graph is a directed graph that shows a state of the system of resources and process, with each process and each resource represented by a node. So here we have a node for P1 and RA. So a graph edge directed from a process to resources indicate the resources that has been requested by the process but not yet granted. So example will be A. This directed graph is requesting but not yet granted. B, within the resources node, the dots show the instance of that resource. So in B, the resources again is granted. The graph edge, again, directed from reusable resources, that's reusable resources RA, is directed towards the process, indicate that the resource has been granted. So again, we may see the examples of this in our future slides soon. So C again is called a circular weight, because circular weights here, we can see that there's only one unit each of resources RA and RB, but process 1, or I'll say P1 holds the RB and requesting RA, while P2 also hold RA but requesting for RB. So we may have the idea of again, circular weighting. But in this case, there's no deadlock because multiple units of each resource still are available. And that's the whole concept here. So that's the circular concept also. So here we have resources RA, or reusable resources, is granted to P1, RB to P2, RC to P3, RD to P4, but P1 have RA is requesting for RB. P2 have RB is requesting for R, then it again goes all the way. So kind of a concept of a circular. So again, that's as we can see, this is a circular weight concept. So the next is the condition for deadlock. So we have 4 conditions here. Sorry, 3 conditions of a policy that we again need to follow. So 3 conditions of policy must be present for deadlock to be possible. So first is the mutual exclusion. So mutual exclusion means, again, only one process may use a resource at a time. No process may access a resource on unit that has been allocated to another process. The next is hold and wait. So hold and wait, again, process may hold allocated resources while waiting assignment of other resources. Then we have the no preemption. That's no resources can be forcibly or forcibly removed from a process holding it. So again, in many ways, these conditions are quite desirable Example would be the mutual exclusion is needed to ensure consistency of results and the integrity of a database. Similarly, preemption should not be done arbitrarily. For example, when the data resources are involved, preemption must be supported by a rollback recovery mechanism, which again restores the process and its resources to a suitable previous state from which the process can eventually repeat its action. Also, we have the circular wait, which is a closed chain of process exists such that, again, process hold at least one resources needed by the next process in the chain, as we saw in the previous slide. So this is circular. P1 have RA is looking for RB, P2 have RB looking for RC, requesting for RC, and it keep going around. So now we need some few deadlock prevention strategy. And here we said again, design a system in such a way that the possibility of deadlock is excluded. So we have two ways of doing this, two methods, indirect or direct. So the strategy of a deadlock prevention is simply put to design a system in such a way that, again, the possibility of deadlock is excluded. Now we can view deadlock prevention method as falling into two cases. As indirect method of deadlock prevention is to prevent the occurrence of one of the three necessary conditions listed in our previous slides, the three conditions, excluding the circular wait. Then the direct method of deadlock prevention is to prevent the occurrence of a circular wait. So again, we can go to the previous slide. The first, indirect, mutual exclusion, hold and wait, and no preemption. Then direct also, we should exclude, prevent the occurrence of circular wait. So a mutual exclusion, here we say that in general, the first of the four listed conditions cannot be disallowed, If access to a resource requires mutual exclusion, then the mutual exclusion must be supported by the operating system. And also some resources such as files may allow multiple access for reads, but only exclusive access for writes. Even in this case, a deadlock can occur if more than one process, again, requires write permission. So again, we say even in this case, the deadlock can occur if more than one process requires the write permission. Also, the hold and wait condition can be prevented by, again, requiring that the process requests all of its required resources at one time and block the process until all the requests can be granted simultaneously. Again, this approach is inefficient in two ways. First, a process may end up for a long time waiting for all of its resources requests to be filled, when actually, in fact, it could be proceeded with only one sum of the resources. Second, resources allocated to a process may remain unused for a considerable period, during which time they are denied to other process. So another problem is that the process may not know in advance all of the resources that it will require. That's the concept of hold and wait can be again prevented by requiring that a process requests all of its required resources at one time, then blocking the process until all the requests can be granted simultaneously. Then we also talk about the no preemption. Here we say that if a process holding a certain resources is denied a further request, that process must release its original resources and request them again. So operating system may preempt the second process and require it to release its resources. So this approach practically only when applied to resources whose state can be easily saved and restored later, as in the case with a processor. So if a process requests a resources that is currently held by another process, the operating system may preempt the second process and require it to release its resources. And the circular wait, again, condition can be prevented by defining the linear ordering of resources types. If a process has been allocated resources of type R, then it may subsequently request only those resources of types following in order. So that is the circular wait condition can be prevented by defining linear order of resources types. Now the next is the deadlock avoidance. So here we say it allowed 3 necessary conditions, but makes judicious choice to assure that deadlock point is never reached. So an approach here is to solving the deadlock problem that differs from deadlock prevention. And that's the deadlock avoidance. So in deadlock avoidance, we constrain resource requests to prevent at least one of the 4 conditions of deadlock. This is either done indirectly by preventing one of the 3 necessary policy conditions, which is the mutual exclusion, hold and wait, and no preemptions, or directly by preventing the circular wait. And this again leads to inefficient use of resources and inefficient execution of process. So again, deadlock avoidance, on the other hand, allows the 3 necessary conditions, but makes judicious choices to ensure that deadlock point is never reached. So this requires knowledge of a future process request. So that will be the conclusion of these lectures. Again, this lectures is part 1 of chapter 6. And our main goal here is to understand the concept of deadlock. And next lectures, we're going to discuss about the concept of starvation. So again, wish everyone the best. Thank you.